that is the Jacobian matrix from S to S1 and S2 we can find with the information. If you solve the problem by hand, it is also okay. So we can find the gradient of this objective function. And then we can use the gradient in the objective function, where the objective function returns two variables. One is the objective function itself. The other one is the gradient of the objective function. So this function will return two arguments. Earlier I said there are two ways to describe the objective function. One is by .m file, which is the way I used here. The other one is by anonymous function. So there are two ways. I recommend this one always. However, for this kind of example, because two variables should be returned, we can no longer use this kind of notation, because this one only allows one to return only one image. So we cannot use this one for this particular example. We have to use .m format to write a function. And this is the one part we have to do to modify the objective function to return not only the objective function, but also the gradient of the objective function. Also, we need to set, there should be OPT. If I use my old code, there should be OPT. I should set the grad obj to on. The default one is off. If I set this one on, it means that we have no the gradient information when described in this function. I used the OPT earlier. Here I have to use OPT again. And in this case, we can get more accurate results because we use the gradient information, which improve the way to search for the ideal result. It should be noted that this objective function is a specially selected function by Professor Rosenbrock. For normal optimization problems, gradient information may not be very useful. It may not be very necessary. We just use the unconstrained optimization problem using the default method. It should come up with a good optimization solution. However, remember that the solution will depend upon the selection of the initial search point. That's the only limitation of the function. Normally, we do not have to use gradient information. For a special case of unconstrained optimization problems, we want to solve a modified version of the problem like this, where there are some constraints on x, but x should be selected between a certain interval of small n and x capital N. So these are the specific limitations or the requirements x must specify first. And here xt stands for subject to, which means that we have x must satisfy this constraint, and then how to select x to minimize the objective function. And there are some code to solve the problem. And there is a f-min search B and D function, which can be used directly. Or this kind of problem can be solved by the constraint optimization problem, which I will explain later on in the course. So there might be several ways to solve this kind of problems. I'm not going to present it now. We can use this kind of function to solve the problem. If you are interested, you can try the code. But I think it is easier to understand. Now, let's move on to another topic. How to solve constraint optimization problems. So before that, we want to make it clear what are the constraints and what are the feasibility region of feasible solutions. And then I shall discuss something about linear programming problems, and then quadratic programming problems. These are two examples of constraint problems which are often used, widely used. And apart from these two special applications, we want to discuss something about how we can find the general nonlinear programming problem solutions. So these are the topics I want to give now. We have brief. Too much maybe. The optimization problem itself might be quite complicated, but here my target is to use the function directly to get the solution.